Okay, now that we have covered the geometric interpretation of vectors, we are jumping onto a very important topic about vectors, namely the vector norm. Let me first start with the boring explanation of what vector norm is. So, vector norm is defined for every vector. Say, let me take this pen. So, for a vector x, it is represented with two vertical bars, like the absolute value, but it's this time it's the 2, and there always exists a little number here. So I'm gonna go with a very generalized number, number p. Typically, the vector norm that you will be seeing is the p is going to be 2. And it's going to be referred to as the L2 norm. And so this is to be pronounced as LP norm. So LP norm of a vector is defined as you're going to take the summation of all of the incidence, all of the indexes, x of I, take the absolute value and take it to the power p for I equals 1 to whatever dimensionality it has, d, and you're going to take the square or p root of this. So I know this might look ugly, but when you replace the p with the p number that we will mostly be using, so L2 norm of a vector is nothing but taking the squares I equals 1 to d x of I squared, like there's actually no need for the absolute, and take the square root of that, and there's obviously no need for that too, mathematically speaking. So when we are talking about the L2 norm in two-dimensional space, we mentioned that, whoops, this was not a very good vertical line. So let's say this is our axis, and we mentioned, let's take some x, this vector to be 1, 2. Notice that I'm always using column vectors to represent vectors, and we mentioned that axes, like vectors, are just points on a space. So x1 and x2 are the indices. So we are talking about 1 and 2. So that's our vector. So our vector, we are saying that vector is just a point, but it's also a vector that you know from physics, like the arrow. And and you guessed it, the L2 norm of a vector all of a sudden becomes its distance, its Euclidean distance from the origin. So x becomes x1 squared plus, whoops, x2 squared. So that's your L2 norm. And there's, of course, let's go ahead and make the L1 norm as well. So if we change the p here, if we make it the L1 norm, so that's pronounced as L2 norm, and that's the L1 norm of a vector, norm of a vector. So you're doing nothing but summing the absolutes, xi. That's it. I equals 1 to d. And for this, let me take another color, the baby blue here. The L2 norm then becomes going to this direction plus going to that direction. So it's mostly sometimes referred to as the Manhattan distance, or Manhattan norm, because just like the streets in Manhattan, if you would like to go from A to B, we're not talking about bird's flight. You're going to take the streets. So this is the distance that you're going to cover to go from from the origin to where this where this vector is showing. So more generally, we're talking about a vector norm, so it's the LP norm. We have what we have is again the boring formula that I shared for L1 norm is nothing but summing the distances, and the L2 norm is the sum of the squares, and LP norm is just like shown in the formula. And let me move my image so that you can have an idea of what L infinity norm would be. So L infinity norm, it's a little bit difficult to comprehend that this is when you replace p with infinity, it becomes all of a sudden max. But when you look at this like this, so when you take p to the infinity, we are summing all of the indices. We're taking the infinite infinite power of all of the indices. So they're fighting with each other. Like if one of them is greater than another, when you take it to the infinity power, all of a sudden this one that's greater just suppresses the next one. This is what happens when you go to infinity. And when you take the root of that, what remains is only the maximum. So of course in math, strictly speaking, the infinity does not exist. I mean, in math it exists, but in physical world it's almost impossible to acknowledge and understand what infinity is. So let's stop it here. Next one, we're going to use this to talk about normalization.